the individual presenters, especially for today's course, since it is a new course. I'm very interested in your feedback. We've worked with, many of you may have seen me before on American Training Solutions. I work with a lot of different trade associations and different companies on trying to convey tools and information that help design professionals make selections according to building sustainability. And so I've had the pleasure of working with BASF on trying to put together a kind of cross-platform program that talks a bit about embodied energy, how you use things like EPDs and LCAs to actually choose products. So hopefully today we'll use an example of rigid polystyrene foam and compare and contrast amongst other insulation foams. And hopefully it'll make sense and you'll be able to learn and apply the various concepts. So the course description is here, but mainly I wanted to dive right into the learning objectives. And before I actually get into those, I wanted to mention that there's a great Dropbox. And so yesterday I uploaded a copy of this presentation, as well as a variety of other tools and resources that discuss sustainability, environmental product declarations. I loaded up a couple of different environmental product declarations. I uploaded also some information from the EC3 tool, which we'll talk about later, where you can compare and contrast environmental footprints from various materials. So let me know what you think about those. I'd love to hear from you. And most importantly, though, item number one, we want you to know about why is all this stuff around energy efficiency and sustainability, and most importantly, carbon, such a big deal right now. So we'll talk about that quickly. I think most of you probably understand that already by now. Number two, we're going to try and help you understand a little bit the various types of CO2, how life cycle analysis rolls into environmental product declarations, and how that rolls into you being able to make great material selections, regardless how you use these tools across any product. Thirdly, we're going to explore a little bit about carbon intensity, and we'll compare and contrast different insulation types and how you might explore one or the other. And then part B, this is like a double one, you get extra credit. We'll talk about how raw material inputs, so whether you're using recycled material or renewable material or biomass feedstocks, how that can actually help lower embodied energy. And then lastly, we'll talk about some tools that are out there to try and make all this stuff a little more straightforward and easier for you. So I think it should be a great class, and I'm really looking forward to hearing your feedback. So objective number one, why in the heck are we talking about all this stuff? Well, as always, it's about heating up the world. More carbon than we've ever had in the atmosphere since we've been measuring this stuff way back in the 1700s. And as you can see, right around industrialization, it seems like things really started to kick off. So you've probably seen this slide before, so I won't belabor it, but emissions in gray on the far right-hand side where my cursor is, and then overall parts per million carbon on the left-hand side. So essentially more and more carbon is going into the atmosphere. So what are we going to do about it? Well, and why do we need to worry about it? Well, a lot of different people, no matter what your politics are talking about, yeah, this carbon thing's a problem. We're having climate disruption, we're having warming planets, all kinds of things are happening. So whether you're in government, whether, Elon Musk is talking about it, former presidents are talking about it, even a president of a big multinational company, like I mentioned, BASF is talking about it. So there must be something up if everybody's worrying about this, right? And what are they worrying about? Well, regardless how it's happening, a lot of things are changing in the world. So we're melting seawater, we're getting sea level rise, we're getting certainly lots of heat waves, the ocean's warming, so we're getting stronger storms, plants are kind of changing the way they're doing things, animals and insects are changing where they're going, we're getting these severe weather patterns, some places are getting a lot drier, some people are getting a lot hotter, some people are burning a lot more, so it's affecting air quality. So a lot of different things going on in the world. And a lot of this boils down to building and construction and carbon. And so we're going to be building a lot of buildings in the next, say, run up to 2050, even by 2060. So as this slide presents, we're going to double the amount of surface area in the built environment by 2060. And so you may have heard this factoid before, but to put it in perspective, imagine the entire surface area of all the buildings in Manhattan essentially being rebuilt every month for the next 40 years. So that's kind of a crazy number, right? So to put that in perspective of why buildings and why are we picking on buildings, so here's a pie chart that kind of shows where all the different emissions from carbon dioxide and greenhouse gases come from. And you can see building operations there, 28%, nominally call it 28, 29%, plus that little pie below, the 11%, which are the materials, all that winds up to about 40%, 39 to be specific. And 39, 40% of all of the carbon comes from the built environment, whether it's when we're building these buildings or whether when we're operating these buildings. So it's more than transportation, almost twice. It's more than manufacturing. And all of us on the call today, if you're part of the design world, the AEC community, we get to help change that, right? So that's what's exciting about the tools in the presentation today. Formally, we've really thought a lot about operational carbon, operational energy, you know, how much heating and cooling are we doing in these buildings? But what we've also discovered is it's really important to think about, well, what is the carbon footprint, the embodied energy, the investment to make all these materials before we even put them in a building? So that's what we're going to be talking about a little bit today. And you may have heard of the 2030 challenge that started back in the early 2000s. So it's a group of people that started kind of scratching their head and thinking, this carbon thing's getting kind of crazy. Buildings are responsible for a lot of it. Let's try and have all net zero energy buildings in operation, all new buildings by the year 2030. If we do that, we think we can curb the amount of global warming that's going to go on. Well, because of the rise and the rapidity of how fast things are going, everyone's beginning to think, well, maybe we don't have until 2030. Maybe we need to do it sooner. And the good news is all of the tools are here for us to be able to do it today. So zero carbon today, how would you work with something like that if it so interested you in your projects? So a couple of people, a couple of different incentives that have happened in North America, here in the United States, federal incentives, and a couple of big different investment acts are really helping to propagate and support this initiative, you might say. So whether it's this Infrastructure Investment and Job Acts that came down, for example, you know, $7 billion for installing EV chargers for people that want to drive electric cars. A lot of other things too in the infrastructure, you know, piping replacements and dam replacements and different things like that. But embedded down in there, $245 million worth of Department of Energy money to help people have resilient, energy efficient codes and then figure out how to implement and train them. So that's very exciting. And then we had this Inflation Reduction Act that came out. And what that really did is, remember those tax credits and those tax deductions that you used to be able to get for building energy efficient construction? And sometimes they were valid, sometimes they're not, they expired. Well, the fun thing about all this now is that whole suite of these pre-existing credits have now been locked in for the next 10 years. So you don't have to worry about, should I really invest my time, say for the 179D commercial tax credit, or actually that was a deduction, pardon me. You can get up to $5 per square foot, depending on how you're designing your particular buildings. That's a lot of money. You can also get it for renovations or roofing and things like that. The 25C tax credit is the home energy efficiency tax credit, which actually goes to the homeowners that want to do maintenance. So you can get anywhere from $2,000 to $5,000 a year for the next 10 years by, you know, replacing some windows 1 year, upgrading your HVAC 1 year, maybe putting in some insulation in the roof 1 year. So that one is continuing. And then also in the residential space, the home builder tax credit, that bottom one, the 45L, and that can get you, say, you want to design to the Energy Star system, you can get $2,500 back per home. Or if you want to design to the Zero Energy, DOE Zero Energy Program standard, you can get up to $5,000 per home. So if that kind of money interests you and your clients, there are some incentives to figure out how to get it done. Additionally, thinking about housing and urban HUD, they have reinvigorated a variety of programs. So the home program, $1.5 billion going into affordable housing and upgrading. The community development block grants, $3.3 billion to go to states and cities for renovating and upgrading different infrastructure, public infrastructure. And then the bottom one there, the GRRP, that's this Green and Resilient Retrofit Program. So mainly how we're here to talk today about brand new construction, a lot of it has to do with maintaining and ongoing repair of our existing infrastructure. So nominally, what, 120 million residences, probably those 120 million homes and multifamily units, probably 60% have zero insulation because they were built before 1980. So those are some buckets of money that are out there kind of getting everybody interested. But it's not just the federal government that's trying to do this. Many times the cities, the states, the counties are all hopping on the bandwagon. And some of these have been around for years. Remember, like LEED, sometimes U.S. Green Building Council's LEED program, National Association of Home Builders launched their National Green Building Standard, ICC 700, probably over 10 or 15 years ago. They've hundreds of thousands of homes have been credentialed to that program. Of course, there's Green Globes, there's Green. There's states like California, New York that are giving incentives and mandating certain things, and even cities like whether it's Los Angeles or Austin or New York City. And then there's these private labeled systems, whether it's things like South Face Institute or the City of Austin program or Washington State's Build Green program. So a lot of momentum about all this. And most importantly, you've probably heard something about energy codes, and energy codes getting a little more advanced. So probably from when we really got serious about this in 2009, and we added to the International Energy Conservation Code the requirements for air leakage testing. So remember the 5 air changes per hour in the warmer climate zones and 3 air changes per hour in the cooler climate zones. And then in the 2012, every 3 years, these codes update, these model energy codes, and we added in continuous insulation and additional improved insulation requirements in both the wall and the roof and the building envelope and even in the slabs. And so 2015, we built on that, 2018, 2021, you might say that we've probably gotten to about the maximum of building energy envelope thermal payback efficiency right now with the 2021 code. There's a zero energy addendum in that code. And the 2021 code's probably about 55–60% more energy efficient than the code was back in 2006, 2009. So the problem is not many states have adopted it. Some states are still on no code. Some states are on, the 2009, 2012. Some states kind of pick and choose what they want. So the main push to this is building codes are the worst building legally allowed by law. So whether it's the commercial space or the residential space, do you really want to build the worst building legally allowed by law? And typically, building codes only get more stringent. And so sometimes it would be illegal to build the same building you built 3 years ago today because the energy codes have changed so much. So it has a lot to do with functional obsolescence and also value of these buildings. So as you can see in the green, it's hard to look at these charts sometimes online, but the PowerPoint presentation is available for you to download from the Dropbox. You can see green like Washington State and California and Vermont, New Jersey. They've adopted the the newest codes, and that's that 13%, as you can see in the little pie chart over there by floor area. So there's still like over half the country that hasn't done much yet. So hopefully they'll catch up. But even if a state doesn't, perhaps a county can, or perhaps a city can, or regardless of what the building code says, you as enlightened building professionals can help convince, as AIA requires for our ethical responsibility, counseling our clients to build great sustainable structures. So with that in mind, let's go ahead and just dip in a little bit this is kind of geeky. I know this isn't a code talk, but I threw this in here just so you can see along the various climate zones. So climate zone 1 starting down in Florida in the warm climate zones, all the way up to say climate zone 3, which is kind of the south, the Mason-Dixie line. And then pretty much everything north of that are the cold climates. And the main thing and the new discussion is all about insulation, increased insulation requirements, whether it's in the cavity. Sometimes the new building codes require so much insulation that you can't squeeze it all in the cavity anymore. And so you have to kind of blanket the building around the outside with continuous insulation, sometimes called CI for continuous insulation. And some people are saying, oh, well, like if we look on line 3 there in climate zone 3, think of, say, Oklahoma or northern Texas, where the walls may have required an R20, or it can say, oh, well, if you can't squeeze all that into your cavity, why don't you just put R13 and then 5 inches of continuous, or an R5 of continuous insulation around the outside, or just forget cavity at all and put it all on the outside. Just have a R value of 15 of continuous insulation with whatever insulation du jour you choose, and you'll be in compliance. Of course, these are prescriptive methods. You can have other ways to meet the code, whether you're doing overall U value calculations or energy modeling calculations. So you can do trade-offs and fancy things like that. But the reason why I showed this is to talk about, as an example, our sustainability journey and tools today. I've selected the theme of rigid EPS, expandable polystyrene or graphite polystyrene rigid foam insulation that people are often using as a continuous insulation around the walls or perhaps under the slabs as our launching point for the discussion today. So that is hopefully the reason why all this is important. So I didn't want to spend too much time on that, but I wanted to set the context of the ship has left the port, the train's left the station, and so now we need to get closer to zero operational energy. And then also, since 11% of all of embodied energy comes from the materials, how do we choose the best stuff to go in our buildings? And how do we know? Well, I'm glad you asked. It's about carbon. And of course, there's a thing called lifecycle analysis. Some people call it LCA. And others talk about environmental product declarations, EPDs, that's driving all this. So we'll dip into what those words mean if you're not familiar with them. But before we do that, I wanted to talk a little bit about carbon. So carbon is carbon is carbon. Sometimes we have carbon that's a few million years old from old compressed dinosaur bones, and it's in the form of oil and natural gas. And sometimes we have organic, biogenic carbon, which grows and has a continuous cycle, and we take oxygen from the air or CO2 from the air and usually turn it into some kind of wood product or cellulose product. So biogenic kind of circulates normally in the atmosphere, and it has for millennia. And then men came along and women came along and all kinds of folks and decided, well, let's dig some of this stuff out that was trapped in the earth and anthropogenically let's burn it. And that's how we got our little balance out of kilter with what's in the atmosphere. Why is that important? Well, carbon dioxide is a great insulator and it kind of blankets the earth. And so we start to heat up because the earth just gets warmer, hence global warming. So those are kind of the two kinds of carbon. And the reason why I talk about that is carbon is carbon. Carbon can be sequestered. It can be locked in, like say wood in a house or a beam. Carbon can also be locked in, even if it comes from the ground, that it's oil or natural gas turned into something like plastic. It's locked into that plastic, so it's sequestered in that plastic. It hasn't leaked out into the atmosphere to cause global warming. So I don't want us to always think that carbon from underground, just because it was 2 million years old and turned into, say, plastic, is necessarily bad. It's just a different kind of carbon, and it's still sequestered there. So just like you burn wood, you could release it, you can burn plastic and release that too. So with that being said, going into operational emissions. So when we build our structures, we heat them and we cool them and we have lights in them. And typically about 70% of all the electricity in the country, in the United States, gets used to heat and cool buildings. So 40% of all energy, that's 70% of all electricity. So you can think about that. Thinking about electricity, in order to get that kilowatt of electricity to your building to be able to use, you've already kind of lost 2/3 of it before it ever got to you. So in other words, every kilowatt that we use in a building is, I had to make 3 kilowatts to start with. So the coal power plant, the solar power plant, the wind power plant, whatever that was, usually those are only 30 or 40% efficient. So you lose, 60% of everything you put in before you get going. And then when you transmit that electricity over the power lines, you lose some losses there. So that is why once it gets to you, you've already lost kind of 2/3 of it, right? So that's why every kilowatt we save is so important, because save 1 and you really are saving 3. So operationally, when we looked at that graph before, about 30% of all of our building CO2 comes from operations, and 11% came from materials. So that's why it's important to think about that way. So we'll talk about that when it comes up in our life cycle. Then there's what we call our embodied carbon emissions. So AIA talks about it a little bit. I think the way I like to think about it, instead of the American Institute of Architects, is think about it as just carbon invested and consumed, these upfront emissions, before you ever start to operate your building. So you've got to build the building, you've got to make the stuff that goes in it, you've got to transport all the stuff to there, you've got to pour the foundations. So all of that really is what we call embodied carbon or embodied emissions, these upfront emissions that happen before you ever even start running your building with electricity. And many people parse these things of, oh, well, it's indirect energy and direct energy. Direct energies, the energy actually used, when I burn diesel in the truck to drive the products to the plant side, versus all the invested energy that when I extracted the raw materials and manufactured that stuff at the factory before I shipped it to the job site. So tomato, it's all energy, and we still need to keep track of it. So why am I digging into all this? Because I'm going to show you a really kind of eye chart here, a complicated chart, because it all starts with what we call life cycle analysis, life cycle assessment. And so kind of looking over on the very left-hand side there, where you see the circles, 1, 2, 3, 4, 5. So normally we talk about somewhere between 4 and 5 phases of life cycle. So in those slices, slice number 1 is, okay, I've got to produce the item I'm going to put into the building. I've got to produce the windows, I've got to produce insulation, I've got to produce the concrete. And they divide that up a little bit. You can see this A1, the raw materials. So maybe it's the Portland cement, maybe it's the polymers. Then I've got to transport that to the factory. So there's an A2 for the fuel and the transportation. A3, I'm actually going to make my widget. I'm going to make my windows. I'm going to manufacture my foam. I'm going to manufacture the ready-mix concrete. I'm going to mix it all together, if you will. Then that's kind of all the way here to the far right. You see that's called cradle to gate. And oftentimes that's where our EPDs or our environmental product declarations stop. They say, oh, well, we're just going to add up the stuff that this upfront embodied energy, this investment to get the products at the edge of the shop floor of the factory before we ship it to the job site. And I'll come back to EPD in a minute, but I just wanted you to get that sense for that's a very small slice of the whole enchilada, or the whole pizza, if you will. Some of you may not have had lunch yet, and you might be hungry, so sorry to tantalize you with a food metaphor. Now, slice number 2 is called the construction process. So we've made our widget, it's waiting at the gate of the factory that made it, and now this, you can see A4, I've got to ship it to the job site, right? So maybe my windows came from Germany and they're super fancy windows and I'm building a high rise in Philadelphia. Or maybe I'm have a bamboo flooring and it's coming from Asia and I'm putting it in my super sustainable, eco-friendly Montessori school in California. I've got to ship it, on a ship all the way over. And then we've got to assemble it at the job site, right? So we have factory workers that are driving their trucks and the diesel trucks, and we got to heat the job site. We have all that kind of stuff going on. So all this up front, you might say, production plus construction, this plus item step 1 and item step 2, all that kind of goes into just getting the building ready to go. Day one, up to day one, so I can turn it on and then start heating and cooling it and having lights. So we transition then into what we call the operational phase, operational carbon. So all of this up front is called embodied energy. And then we have the use phase, which is this item number 3. And the use phase can be things like B1, I'm using the building, I'm using the materials. B2, I have to maintain the building, I have to maintain the materials, I have to change the shingles on the roof, I have to change the EPD and membrane, I have got to shampoo the carpet. Occasionally, I have to repair and replace things, B3, B4. Occasionally, I'm remodeling, I'm ripping things out, moving walls. In commercial construction, that probably happens, what, every 8 to 10 years, if you're in a hotel or something. And then there's the things we think about more typically. I've got to pay the electric bill, I've got to pay the water bill, I've got to pay the gas bill. So that's the operational energy. So you can see there's a whole lot more B1, B2, B3, B4, other than just the electricity in the building in this quote unquote use phase. And all of us as design professionals get to impact, well, what am I specifying? Does it need to be replaced very often? Does it need to be repaired very often? Am I specifying tile floor, which doesn't have to be shampooed or waxed? Or am I specifying carpet that maybe has to be shampooed every 5 to 8 years? I'm maybe tearing it out and putting in new carpet. Maybe they're carpet tiles. So all of that is in this area. And then of course, B7 is water. Water, you may think, yeah, it's the toilets, it's the water fountain, it's, you know, washing my hands, but also operational water is the water for the HVAC systems. If you're in larger facilities where you have heating and cooling going on, you have a water tower perhaps, that's all that in that area. So all of this winds up being what we call, to the far right here, cradle to grave. So you've got cradle to gate, I made the stuff and it's at the factory. And then from the gate of the factory, I take it to the job site. Then once we're using it and we're operating the building, 30, 60, 80, 100 years, we have what's called cradle to grave. But that's only part of the story. So what am I going to do when I am taking that stuff out to replace it? What am I going to do when I'm going to tear the building down? What am I going to do when I'm going to rehab the building? Well, that's where you get to this number 4 here that talks about end of life stages, right? So you have C1 here, deconstruction. You have C2, transportation. You've got to haul it to the landfill. You've got to haul it to recycling. You've got to do something with that stuff. C3, waste processing. So maybe I'm burning it for waste to energy. Perhaps I'm starting the process of thinking about maybe recycling or reusing it. And then C4, I'm putting it in the landfill. And on many of my other presentations, I always talk about, usually we do a little thing where people enter in the chat box, you know, what percentage of construction debris do you think fills up all the landfills? But for sake of time today, I won't do that. But I'll tell you the answer. It's over 50%. Over 50% of all the stuff in our municipal landfills is construction debris. So that's on all of us, right, as professionals in the construction industry. So how can we get around that? Well, that's this very rarely talked about item number 5, and that is the D for reuse, recover, recycle. So remember way back, you know, when USGBC started, US Green Building Council, and we had the first version of LEED back in the late 90s, the early 2000s. And we used to talk about a couple of things. We used to talk about, well, are you using something within a 500-mile radius of where your project is? So, well, that is A4, gate to site transportation. You wanted it to be somewhat close, so it wasn't marble imported from Italy or special windows imported from Germany. So LEED was thinking about this stuff really early on. But additionally, remember, as we think about down here, recycle, getting points for recycled content, getting points for reuse, getting points for not tearing down the whole building and reusing part of it. That's all here. And what I'd like to call to your attention over in the right-hand column here, cradle to gate, C to C. Many of you may remember the renowned architect Bill McDonough, who wrote a book, Cradle to Cradle, and essentially talking about the world of building construction, kind of like the world of food, right? Where we grow food, we harvest food, we eat food, we poop food out, and that waste becomes, you know, fertilizer, and it comes right back to the beginning and we start all over again. Well, this virtual cycle of cradle to cradle, essentially nowadays we call it circular economy. And so that's what we should all try to espouse to and figure out, well, what are we going to do with all this construction waste and debris? There's great embodied energy trapped in there. How can we not lose it all? So I hope this wasn't too dense for you, but I think it's really important that you understand it's complicated. It's a lot about accounting, and there's lots of ways to game the system. So you, as astute specifiers of products, want to make sure that no one in their marketing is trying to hoodwink you and maybe say, oh, I have this great EPD. It's a cradle to gate EPD, environmental product declaration. It tells you all of the environmental sins and burdens on the environment for my product, but just A1, A2, A3. So that'd be kind of like, right? Not the best kind of full way to compare the full burden of one product to another. You at least want to be able to have the construction process in there, the full embodied energy. And I'd say you really want to be able to have the cradle to grave, because if you're specifying things that are going to need to be repaired and have maintenance on them and replaced often, you know, maybe you have wood shingles because you're a naturalist and you don't care about fire and the bugs eating the wood shingles on your roof or your wood siding, where you're going to be, you know, turpentining those, painting them. You're going to be probably replacing them if there's a fire. The bugs are going to eat them, the termites are going to eat them, versus say maybe a hardy board or a cementitious siding, which says a super high embodied energy up front, but you're saving here. So you can start to kind of see it's all about accounting, and it's all about, well, what is your project? What is your programming? What is your environment? Are you in a dry environment? Are you in a wet environment? Are you in an environment prone to corrosion or prone to fire? So there is no one best material depending on where you are. So enough about that. Let's move on. So a life cycle analysis is kind of taking that whole step that we just saw here. It might take 6 months to do a life cycle analysis for a product, and it may cost $30,000 to $50,000, and you get a 100-page report. And so you're kind of scratching your head and thinking, okay, Jack, what in the heck am I going to do with this 100-page report? Well, coming to your rescue is the EPD, the Environmental Product Declaration. And essentially, it's the Reader's Digest condensed version. It's the Cliff Notes. It's the summarized executive summary of everything that's in that LCA, but as it pertains to the environment. So since we're kind of talking about carbon, EPDs are talking a bit more about the environment and not so much about, you know, the operational safety per se of the building or the indoor air quality or something like that. It's more, you know, addressing that 11% of our pie of materials, and also, if we do it right, the operational phase of the building. So when you look at an EPD, you want to make sure that it's based on a life cycle analysis of as many of the phases as possible, including the use phase, and maybe even the end of life phase and the recycle phase. Because if you have something like, say, asbestos, yeah, it was put in a long time ago, but it's going to be expensive to get rid of that. You're going to have the remediation. And so it may have operated great and been encapsulated and not hurt anybody, but on the end, it's going to be very laborious to take care of that. The middle concept here, PCR, product category rules, essentially what that allows you to do is compare apples to apples comparisons. So the industry gets together. The flooring industry has a PCR, a set of product category rules, to be able to say, hey, all flooring is going to be compared this way with this amount of, you know, 1 square meter of installed floor area. Or the wallpaper industry does the same, you know, one square meter or 1 square foot of painted surface. Installation talks about R value, the installation R value. So you want to make sure to be able to compare that your product category rules, or quote unquote your functional unit, is the same, and then you can compare things. So EPDs are our friend. EPDs are great for carbon reporting. There's different kinds of EPDs. Some people just do their own EPD and they say, trust me, believe me, it's really true. That's a type 2 EPD. Type 3 EPDs actually get verified. So someone comes and really looks through all the information that you put it in the system. So that's the nice check mark on top. And more, these environmental product declarations are included in these green rating systems, whether it's green globes or the LEED program or the European, British Green program, Green Star. And then of course, many states also are starting to ask you, as well as the federal government and the General Services Administration, to have EPDs for your various products. So with that in mind, what does it look like? Well, here's just two that I cut and pasted from the internet. And one, since we're going to be talking about, as an example, graphite polystyrene foam, I downloaded that one. And then there's also that, so that would be a product specific EPD. So one company tells you all of the inputs and all the environmental burdens that their product creates over a certain number of years, and then maybe you tear it down and haul it to the landfill, or maybe you tear down the product and you recycle it. So all that will be in their EPD. Or you can have what we call on the right-hand side an industry-wide EPD. It's an average. So in this case, the Vinyl Siding Institute got together and they did an EPD, and they averaged all the information from 20 or 30 of their manufacturers across the country. And so you have an average of what in the United States all vinyl siding does, or insulated vinyl siding in this case. And the true power is combining both of these together. So let's say you get an industry-wide insulation EPD for insulating foams, and then you can compare a company-specific one, and then you can say, gosh, am I better than the average? Am I worse? I want this company that does better than the average. And so that helps you compare and contrast and specify products to meet your goals. So real quickly, this isn't an EPD class, so I just wanted to talk about developing the EPDs. So as we talked about before, in that very first square over here, you figure out, well, what product am I talking about? I want to see if there is a set of product category rules for it. So which stages does everybody agree? What unit are we of measurement are we going to be comparing? How long are we comparing it for? What's the life cycle use phase time? Is it, for 10 years, for 25 years, for 100 years? Does it include the recycle or not? All 5 phases. Then you do a life cycle analysis, and once you do your study of all of those phases, you come out with a great big thick report, and then you can create your environmental product declaration. And you can do it yourself for type 2 EPD, or you can have it audited by a third-party provider to make sure you really did it properly. That's called a third-party verified type 3 EPD. And you have your EPD, they're good for 5 years, and you have all these different program operators that can do this for you. So whether it's BASF or Sustainability Consortium, ULE, Underwriter Laboratory Environmental, that used to be the Green Guard Indoor Quality folks. ASTM does them, Carbon Leadership Forum. A lot of people do these. HubSpot, or EPD Hub. So that gives you your EPD. So I've been chatting a lot. I'm sorry, it's my first time for giving this course. So I want to make sure we get it all in. So I'll take a breath. And Kelly, we have a little survey to come up, right?
Sure do, yes. And there it is on your screens now, everyone. So true or false, a life cycle analysis is based on an environmental product declaration. Very good, thank you. See those answers rolling in?
This is usually where Kelly and I always joke. I have this hokey karaoke Jeopardy music that I usually hum along, at least in the first kind of do 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 do.
That's pretty good.
Make the time pass, right?
Yeah, no, that took it up. We have just a couple seconds left here, so I appreciate that. All right, let me close this up and see what you all said. Okay, so we had 30% of respondents saying false, with 70% of respondents saying true.
70% true. So, dun, 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 it's actually false. So it's just the opposite, right? So we do our life cycle analysis first, which is big and long and complicated. We get this 100-page report, and then from that we extract out the Reader's Digest condensed version, and we get like a 6 or 8-page report called an EPD. So this would indeed be false. So I'm sorry, it's a little bit of of a tricky way to word it there. But LCA comes first, and hopefully all life cycle stages, all 5 of them, and then we have a really great EPD. So with that in mind, let's go ahead and go on to the next one. And I'm not going to ask you question number 2 afterwards. As I said, this is a new course, and I think question number 2 is a little hard or maybe disingenuous. What 2 types of EPDs are, name 2 types of EPDs. So the first one is, well, you can have an industry-wide EPD or a manufacturer-specific EPD, which is true. But you can also have what's called, and this is more granular for the geeky EPD nerds like myself, you can have a type 1, type 2, type 3 EPD. So if you just create your own EPD and do it yourself and publish it, it's called type 2. You didn't have anybody verify it. If you have a type 3 EPD, which is the gold standard, then it's been third-party verified, follows the ISO procedures, and it's good for 5 years. So really the true question, the true answer is C, all of the above. So I'll give that to you guys for free. Alrighty, so we've gone through a lot of this stuff to kind of get to where, well, how do we use these tools to do something like compare the carbon intensity of a common insulation material? And then once we compare that, then how do we say, well, gosh, here's a manufacturer that is substituting some of the raw material ingredients with renewable or recycled. How does that change things? I'm glad you asked. We'll see. So let's divide this screen into 2, and let's look at the right-hand side here. So if we're considering like rigid polystyrene, graphite enhanced polystyrene, or just polystyrene sheathing in general, foam sheathing, one of the concepts that you have to remember is sometimes you get more R value with less material. So the density of a material or the amount of weight of a material directly affects its environmental burden, right? So if it takes 5 pounds of something to do the same job and you can do it in 2, well, you use less material, so you actually have a lower environmental burden. So in the case of, say, graphite enhanced expandable polystyrene, EPS, graphite enhanced EPS actually has a higher R value for the same density. So what that means is I can use less of it and still get the wall insulated the same amount. So in this example, you see the little house here, and 1 ton of graphite enhanced polystyrene, in this case Neopor from BASF, can actually give you 450 square meters of insulation on the side of the house or the building at the same R value as if you use a ton of the white EPS foam that's not graphite enhanced. So you'd only be able to get, say, 300 square meters, and that square meter is about a square yard, so you can think about that, or 10 square feet. So you don't quite finish the building if you chose to use the white stuff as opposed to the gray stuff. And so the concept that we're trying to say here is if you can do the job with less material, it's more sustainable. You have a lower environmental footprint, right? So that's kind of as we go over here to the left-hand side where you see lower density sometimes with the same R value also means less carbon. So comparing the gray EPS foam to the white EPS foam without the graphite in it, the gray foam has about a 50% less carbon embodied content. So that's really amazing. So that's kind of the idea. So I'm trying to tie it back to what you would look at in an EPD and what it really means in real practical terms. In the third, in the middle red box here, you see GPS foam, graphite enhanced polystyrene foam, has 30% less mass value than extruded polystyrene foam to do the same job. So in this case, that's the example of what we saw in the houses before. You can use less product to get the same R value, so it's kind of a more sustainable solution. And then lastly, the R value of a GPS foam with the graphite in it is about 25% more than an EPS foam. So it's kind of dense. So I'm trying to just illustrate to you that it gets into the weeds here and it gets a little complicated. And so I'm going to show you this crazy table, which you can generate of all foams, whether it comes from a tool like the Embodied Energy Carbon Calculator and construction tool, or in this case, this came from a study from KPMG Architects, a real recent study where they were actually trying to figure out, well, gosh, there's all these foam options out there. What should I do to insulate my structure? And how do I know, for the same R value, which one has a higher global warming potential or embodied energy or carbon? So this very far right column kind of shows in descending order this styrofoam extruded polystyrene has a lot of carbon there. So 100 kilograms of CO2 equivalent per square meter of installed foam. And then you can kind of follow the way down. Some have 60, some have 9, some have 4. Regular white EPS foam here has more or less 3, that's 2.78. And if you just change the recipe a little bit and sprinkle a little bit of graphite in there, you get this neopore graphite enhanced polystyrene form with 50% lower embodied energy. And then you can do things like fiberglass or blown in cellulose. So fiberglass is usually recycled glass, and cellulose is usually recycled newspaper. Also, recycled newspaper means it's cellulose, so it's wood pulp, so it's biogenic, so you get a credit there because it has embodied energy. So what would you do with something like this? Well, if you're a geeky engineer like me, you can make a little graph. And so let's look at the graph first. So essentially what we've done is we have our total carbon emissions over here of all the material, and we have R values here on the horizontal axis, on the bottom horizontal axis. And we had all of our different foams from that previous table, and we said, well, gosh, what if we come out here to 30? I want an insulated R value of 30, and what would be the total embodied energy for a solution of 30 on my wall or my slab or my roof? So you can see a whole bunch of the lines are clustered here together, all way below 100, maybe even below 50 kilograms of carbon for that 1 meter by 1 meter squared installed, versus these taller ones, which are like extruded polystyrene from various different companies. And even kind of the old recipes versus the new recipes, they're changing out their blowing agents. And so these blowing agents are getting less burdensome to the atmosphere. So they actually make the foam look better. So you'll be able to, say, okay, that's interesting. And so these on the bottom are so banded together here. Even if you go all the way out to 40, you can see in this little expanded view, they're almost all about the same. So let's say, okay, higher density foams, which extruded polystyrenes and polyurethanes typically are, versus these other foam insulation products, shows that's why there's more carbon, right? More product to do the same job, R30 in this case. Now let's look at it another way. So let's say, okay, yeah, I have all this carbon that I've invested in insulation. So now let's graph on this vertical line, the x-axis, how much carbon embodied I'm starting with, and how long do I need to operate my building to save enough, because of the insulation, to save enough energy to pay back for what I invested to make this product. So remember, embodied energy up front in the material, and then I've got to operate my building, and hopefully, because I added all this investment of great insulation, I can reduce the amount of operational energy and gas that I need, and that savings helps me kind of counteract or return on investment, pay back what I started with. So here you can see, gosh, the extruded polystyrene foams are starting into deficit, way of this minus 200, minus 400, and whereas the lower versions of the insulations are all here in kind of like the less than 1 year, less than 6 months kind of frame. So in this little box, I kind of exploded the view over here, and you can kind of see more or less they're all about the same, less than 6 months. So this is how you would use operationally the power of something like an environmental product declaration to say, oh, wow, I'd have to operate, if I choose these yellow products, 9 years before I just break even. Or if I'm using this other product, it takes me almost 16 years just to break even. And that's what Architecture 2030 is talking about. They're like, we don't have time sometimes to build these zero energy buildings that are all tricked out with all these high embodied energy materials to run the building long enough to pay back through savings all the energy it took to make them, and still not blow past our goal in 2050 or 2060. So that's kind of the power of this kind of stuff. So that's why it gets kind of exciting. I know it's kind of dense, but just to kind of start wrapping it up here, biomass, if we think about Recycled ingredients, how can I lower the embodied energy of one of my materials? Well, I can do some things like use biomass in front of it. I can use bio ingredients. I can use other kinds of carbon that are going into my products as raw materials instead of, say, something from the ground like oil, natural gas, or coal. So photosynthesis, as we talked about earlier, it's biogenic. It just takes the carbon that's in the air and puts it in the product. But we also have all this other stuff over here on the far right-hand side, different types of biomass. So, corn crops, garbage, wood from trees, gas that comes from landfills, alcohol maybe that comes from fruits and grains. All of those can actually become raw materials for our various manufactured products. So that's where some companies, and in this case, this bio recycled material is being used as an input to displace oil and petroleum products to make expandable polystyrene. This company, in this example, BASF is using. So they can do renewable feedstocks, biomass, or they can utilize recycled stuff. So remember on our life cycle chain, cradle to cradle, waste equals food, we can take the buildings after we tear them apart, and actually, if we can't reuse that stuff, we can roll it back into our manufacturing process and start again fresh with things like tires and trash and old plastic and foam. So what that really kind of looks like just in a manufacturing process, if you're going to, in this case, be making expandable polystyrene graphite, you'd have your feedstocks over here on the far left-hand side, and you could be using oil or natural gas, or you can do bio products, right, that we just talked about. It could be biogas, it could be different recycled materials that we're crunching down and using in our crock pot when we're making our polymers, and then when it comes out, you can have perhaps the same recipe that doesn't have the biomass, or you can have the recipe that does have the biomass. And so essentially it's the same plant, the same facility, and they just through percentages say, gosh, if I put in 50% raw materials that were natural, then 50% of the product coming out of the plant, it gets to take credit for that. So it's all third-party verified. And this is quite common. You will remember when we looked at things like forest stewardship, FSC certified forests and things like that. There was a chain of custody. And so you can actually have verified, someone looked at this, that they're not trying to do a marketing thing, say it's there. So what does it really mean? In this particular case, you can have on the left-hand side, the regular version of GPS, graphite enhanced polystyrene, in this case called NEO4, and it used to have 2.37 kilograms of carbon, that's embodied energy. Or if you use the bio products and the waste products to go into the cracker when you're cooking it and making the polymer, you fall all the way down to this 0.34. So that's 80% less. So think of it in the same way as fiberglass bat actually comes from ground up Coca-Cola bottles and regular bottles. Blown in cellulose comes from recycled newspaper. Well, in this case, you can have polymeric rigid foam coming from recycled content too. So what does that really mean? Well, if you put it on a scale of, say, hey, normally this stuff comes in one big box called an octobin. It's about 1,000 kilos, 1 ton per octobin. If you saved 2 octobins, 80% less, what does that really mean? So, okay, I have 2,000 kilograms or 2 tons. What is that equal to? Well, gosh, I could drive a car for 3.6 days nonstop. That's what I could do with that 2 tons. Or I could operate a house for 2 months. That's what I could do equivalently with that two tons. I could run my TV for 2 years. Talk about binge watching, right? You can run a compact fluorescent light bulb for 20 years almost. You can fly 4 minutes in a 747. So I put these in there just to kind of give you a frame of reference. I could produce a little bit of beef. So it helps us compare, what is that? So in my last few minutes here, I just want to wrap it up and we'll talk about some tools and what this really means. So a lot of tools are out there. You may have heard something called a carbon calculator tool, the Embodied Carbon Calculator and Construction Tool, EC3. They are part of the tally tool, which is whole building life cycle analysis. So imagine if you have an EPD for every product in the building, and you say you do that for 20 or 30 years, you can add up all of the inputs from these, 10, 20,000 products that maybe go into a building and get a whole building life cycle. All of these other tools that you use out there, whether it's the beam calculator that's used for residential construction or BIM Smith, Master Spec, you're familiar with these. Since this is a new presentation, there's another way to look at it. I think this maybe makes a little more sense. The microcosm, the galaxy of how this stuff fits together. So we have all these tools that are working out there. They're kind of sending information to the EC3 tool or the tally tool, so we can try to get to a whole building lifecycle analysis. And then we have these plugins where it goes to, say, Revit or Bentley or some of these others. So that's how all this stuff, database by database, is coming together through our embodied data files. Once you have all these EPDs into a tool like the EC3 tool, here, we entered and we said, hey, let's look at the EPDs for rigid foam sheathing. And you'll get a big giant list like this, various companies. You can come over here to in the first middle red line, kind of showing you the different types of insulation. So it's like, hey, I want to use rigid foam sheathing on the outside of my building. What kind should I use? Well, you come over here to the third arrow, or the second arrow in this next to last column, and you can see all the embodied energies, and you can actually categorize those and file them and say, okay, well, here's the average for the industry, and here are these companies, some are above and some are below, and that's how you would use a selection tool to choose, in your case, whatever you wanted to have the lowest embodied energy foam. So as we're wrapping it up here, I know this has been kind of dense, but thanks for hanging in there with me. Let's do another little quiz survey here, Kelly.
Sure thing. And there it is. What percentage of embodied carbon was saved using the biomass graphite polystyrene insulation versus the conventional GPS? That's a mouthful, isn't it? 30%, 50%, or 80%? What's that, Jack?
So how much did you save by putting in biomass and recycled stuff into the crock pot when you're cooking up and making polymer? 30%, 50%, 80%? As we get close to lunch, right, it's easy to have a food metaphor.
I mean, we love a good reframe. All right, let's close this up and see what everyone said. Okay, oh, interesting. 26% of respondents said 30%, 36% of respondents said 50%, and 38% of respondents said 80%.
So I know it's hard, so many numbers, maybe it's not really a fair question. But for those of you that got it right, 38% of you did, 80%. So the whole idea, remember, is by substituting the raw material inputs into the manufacturing facility with trash and agro waste and recycled content, you can lower the embodied energy of the same foam by 80%. So that's really, really significant. So it's just like, say, blown-in cellulose does with recycled newspaper, and fiberglass vat does with recycled glass bottles, or even Portland cement does by putting fly ash instead of the Portland cement. So I think since we're close enough to the end, we will skip question number 4. I will tell you that the right answer is, in case you're just dying to know, and some quick resources. So of course you can go to the American Training Solutions Dropbox, which I highly recommend, and this presentation's there, plus a lot of other some downloads for you. Or you can go to the neopor.basf.us website if you want to learn more about graphite enhanced polystyrene foam, and there's a variety of other resources here for you too. So since we're almost at time, I wanted to save a little bit of time for some questions if there's an opportunity, and hand it back to you, Kelly.
Thanks, Jack. Quickly, I did check in the Dropbox folder, and it looks like maybe we put those documents somewhere else. So if you don't mind checking that again when you sign offline.
Okay. I thought I uploaded them all to the right folder, but okay, I'll check. I'll make sure they're there by the end of the day. Kelly sent me a link, and maybe somehow my Dropbox capabilities aren't always the best. So
I mean, you never know. It's technologies like that, but I just want to make sure if anyone did.
thank you, because yeah, I loaded about 8 or 9 different files last night, and also a new upgraded version of the presentation to replace the one that you had put there for me. So I'll check into that.
Awesome. Yes. So the moral of the story there is, everyone, end of the day, we will definitely have those there for you. All right, let's see, a quick question here. First one, someone was interested to find out that some states have no energy code. Is that that's just the way I'm assuming it's structured in the US?
Can we say Idaho? Can we say Wisconsin trying to repeal theirs? A lot of states just kind of don't get it. And sometimes then the individual cities can say, okay, our state's a little crazy, but in our city, we're going to do it. But then you have states like Texas that say, nope, nobody can have a more stringent code in their city than the overall state says. So it's politics. It can't be mandated, but you as engineering professionals and design professionals can design your buildings to whatever high standard you want. Remember, code is the worst building legally allowed to by law, and that's nothing to be proud of.
Okay, awesome. And actually someone else here is saying that they can see the document, so maybe it's an issue on my end, but we will sort that out.
Good, yay, I've been vindicated a little bit, maybe. The queen of technology didn't see it, so.
Oh, no,
I feel like there is hope for me, Kelly, as a non-digital native.
There we go. All right. What are the fire rating properties?
So, like all foams, all these pass the same, 1 hour and oftentimes 2 hour fire ratings. You can actually look to each of the, you can go to this particular company and look at their spec sheets, and you can see their various fire rated assemblies, factory made sure, UL. They're all, obviously they have to meet the fire code. So the NFPA, the standards.
Okay. All right, great.
Smoke toxicity, flame spread, all that, all those tests that Underwriter Laboratories typically performs, they're all available.
Perfect. All right, we probably have to get moving on here to the break, but I do have.
Let me just make a plea. Thank you for your patience. This was a new presentation, so I wasn't sure the right rhythm, and maybe if we have too much squeezed in here. We're calling this an intermediate class. I'd be very interested in your comments to tell me if you think this is intermediate or if this is advanced. I don't think it's beginning, but I'd like some guidance on what you expect from an intermediate class versus an advanced class, because AIA is not real straightforward of how we should score these things. And any hints for making it better?
Perfect. All right, great, Jack. Well, it's always good to see you, and hopefully we'll see you back.